All right, so let's go ahead and take a little detour and think about some fundamental forces. Because inside of the atom, we have one of our fundamental forces at play, but it's one that we haven't specifically talked about. We have talked about another fundamental force, and that is the electromagnetic force. And when in thinking about the electromagnetic force, we have Coulomb's law. Coulomb's law tells us that F equals 1 over 4 pi epsilon naught times Q1 times Q2 all over R squared. All right, so quick refresh. This is one charge. This is a second charge. So if we had an electron as one of our charges and a proton as one of our charges, then we could do this calculation. This mess over here, this 1 over 4 pi epsilon naught, 4 pi, the force is radiating outwards in these concentric circles. And the epsilon naught is the permittivity of free space, typically. It could be the permittivity of water, if that's what we're dealing with, but typically we'll use this as free space. And all of this stuff right here is condensed down into Coulomb's constant, which is at 8.99 times 10 to the 9. And then the electrostatic force is an inverse the square magnitude as you get farther away. So as you get farther away, your magnitude is decreasing a lot quickly. And as you get further and further away, because of that squared, it gets low very quickly. Remember that opposite charges attract. So if this is an electron and a proton, then we would have a negative force. If they are the same, like charges will repel. So this is negative and negative. Then our force becomes a positive because it's pushing us away. All right, so the four fundamental forces are the strong nuclear force, the electromagnetic force, gravitational force, and the weak nuclear force. So in ranking these from strongest to weakest, strong nuclear is 1, electromagnetic is 2, weak nuclear is 3, and then gravitational is 4. Gravity is the weakest, and the strong nuclear is the strongest. And then if you needed to decide which two were stronger and weaker between the electromagnetic force and the weak nuclear force, then the weak nuclear force is weaker, so the electromagnetic force is stronger. So this is the weakest. Now, the strong nuclear force, this is what's at play when we're inside of an atom. If you think about how can you have a helium nucleus, remember helium has an atomic number of 2. So with an atomic number of 2, that implies there's 2 protons next to each other. Well, we just said that like charges repel, so how can these two things be stuck together? The answer to that is the strong nuclear force. The strong nuclear force acts as this Velcro between these two. And it's insanely strong, considering how small it is. But, so one thing to know, very strong. And the downside is it's a very short range. So while the electromagnetic force and the gravitational force have a range of infinity, they act at all distances, the strong nuclear force has an extremely small range. Once I take this proton, I forcibly remove this proton, and now I have a proton over here and a proton over here. Strong nuclear force is no longer in play. Now it's something else going on, the electromagnetic force. Strong nuclear force only acts when the two objects are touching. The two charges are touching. Object. Now, of course, in that helium atom or nucleus, we also have 2 neutrons here, right? So there's our complete nucleus right here. Well, why is it 2 neutrons? What happens if there's 3 neutrons or 8 neutrons? If something is off and you have a whole bunch of extra neutrons, this is what we would refer to as an unstable atom, or specifically an unstable nuclei. An unstable nuclei happen when there are more neutrons than there are protons. So neutrons serve as this buffer between the repelling protons, because not all of these protons can touch, right? So the neutrons act as this buffer. Strong nuclear force is still going to be at play, still holding this big jumbled pile of charges together. But if there are more neutrons than there are protons, then we start seeing, if we graph them, we've got the neutron number and the proton number. This blue line here, this is your line of stability. If it's a 1-to-1 ratio, that means N equals Z. That's the red line here. As you get more neutrons than you have protons, your stability is going to be off. And when you have unstable nuclei, bad things happen. Like radioactivity. Radioactivity is a process where unstable elements decay into new elements and release energy as particles and or waves. Waves like light waves. All right, so think about this for a second. How many words come to mind when you hear the word radiation? When you have your list, think about the positive ones and the negative words. Okay? And now, the next video is going to be this video here, the most radioactive places on Earth. Just fill in this as you watch along.